My talk today will begin by covering the motivation for using mid-infrared detectors, followed by the commercial state-of-the-art in infrared detectors, and then previous work that has been done employing MEMS resonators to try to improve upon this. I'll then go into the design and analysis of our detectors, which are hybridization of aluminum nitride MEMS, resonators, and the metamaterial absorbers, and then also discuss our impedance-based resonant readout. Finally, I will show our measured results and draw some conclusions. Okay, so in recent years, there's been a growing demand for mid-infrared detectors in a wide range of applications. These applications include gas sensing, where high selectivity sensors are required in order to differentiate sharp absorption peaks for gases such as methane from surrounding gases. They also include night vision applications, where high sensitivity detectors are desired in order to differentiate or provide good contrast between objects at similar temperatures, and as well as thermal tracking applications, where fast thermal detectors are required in order to track fast-moving objects. And so infrared detectors can generally be broken into two categories: semiconductor photon detectors such as mercury cadmium telluride, and thermal detectors such as bolometers. In general, photon detectors exhibit high sensitivity and fast speeds, but require cryogenic cooling in order to maintain that high sensitivity, which is bulky and expensive. On the other hand, thermal detectors can operate at room or even elevated temperatures without significant degradation in performance, but have relatively lower sensitivity and slower response. And so currently people have the option of either high-performance detectors or low-cost detectors, but in general they want both. And so there's a desire for improving room temperature detectors while maintaining the low cost to the point where they rival the performance of semiconductor detectors. And so in recent years, there's been some work done employing MEMS-based resonators to improve thermal infrared detectors. And so typically MEMS detectors exhibit fast speed due to their low thermal mass, low noise for high quality factor resonators, and high thermal sensitivity due to the intrinsic temperature dependence of resonant frequency. And so some of this recent work has been in quartz and gallium nitride, and they've shown fast speeds and high sensitivity, but they employ broadband absorbers, which is not ideal for applications such as gas sensing. And so more recently, the Rinaldi group at Northeastern has shown some spectrally selective detectors based on aluminum nitride MEMS. And these detectors have two components. One is this plate, and this excites mechanical vibration, and the other are these areas filled with metasurface filled with dots that has high spectral selectivity and absorption. And so our work involves a similar combination of aluminum nitride MEMS and Metamaterials, but we seek to fully couple the optical and mechanical performance within the entire resonator. And so our detector is shown here, and it consists of bottom platinum electrodes, an aluminum nitride thin film, and top aluminum electrodes. And each of these layers has a dual purpose, one in the optical and one in the mechanical domain. And I'll go into that in the next couple slides. We also have additional features, such as meandering our top electrodes into a continuous trace. And this allows us to apply current to the ends of the trace and resistively heat it, so that we have an additional means for characterizing the thermal response of the detector in addition to laser heating. We also employ an impedance-based readout, and we feel that this has a significant advantages over frequency-based readouts, and I'll go into that later as well. So in the optical domain, our suspended film stack serves as a metamaterial which impedance matches incident infrared waves to minimize reflection and maximize absorption. And this impedance matching is done by setting the effective permittivity and permeability of the film stack, which is in turn set by the thickness of our aluminum nitride and our top electrode dimensions. And so for optimized dimensions, we're able to achieve near 100% absorption at fixed wavelengths. And these peak absorption wavelengths are predominantly set by the width of the top electrode. So here I've shown a cross-sectional view of a single period of the resonator for a single period of the top electrode. And you can see how almost all of the magnetic energy is maintained within the resonator, and this is true of the electrical energy too, electric field as well, but we only show the magnetic field here. And that's what enables us to get this near 100% absorption. Now in the acoustic domain, we apply an RF signal to one of the bottom electrodes and we ground the other. And this induces a time-varying electric field within the aluminum nitride. The top electrode serves to orient this electric field vertically to excite acoustic vibration via the D31 piezoelectric coefficient, shown here. And this vibration has a resonant frequency, which is dependent on the phase velocity and the pitch width. And so we choose a resonant frequency of 33 megahertz, and this gives us our resonator dimension, our general resonator dimensions. And so the acoustic resonance of the acoustic vibration corresponds to an impedance resonant response as well. And this impedance resonant response can be modeled by the equivalent circuit shown here, where C naught is the static capacitance and CM, RM, and LM are the motional capacitance, resistance, and inductance respectively. The impedance is therefore the parallel combination of the motional static components and is a function of frequency, the resonator quality factor, and the temperature. And we leverage this temperature-dependent impedance as our sensing mechanism. So as infrared light is absorbed, the resonator heats up, and this causes a decrease in resonant frequency as the material soften and thermally expand. This is characterized by the temperature coefficient of frequency, which we measure to be minus 39 parts per million Kelvin. And as the resonance shifts downward at a fixed observation frequency, we can detect a change in impedance, shown here. And we choose our observation frequency to be between series and parallel resonance, where the transition in impedance is sharpest. And we characterize this impedance response with what we call the temperature coefficient of impedance, which is the percentage change in impedance with respect to temperature at a fixed observation frequency. This TCZ is analogous to the temperature coefficient of resistance, TCR, of microbolometers, but with one specific difference that is advantageous. So TCR is largely fixed in microbolometers, but the TCZ can be significantly enhanced in high quality factor resonators. And this allows us to significantly enhance the TCZ and therefore sensitivity. And we can show this using our detector readout, which is shown here. So we input a low power fixed frequency observation signal through a hybrid coupler to our MEMS detector, where it's reflected based on our impedance mismatch. The reflected signal is passed back through the hybrid coupler to a commercial power detector, which outputs a voltage based on the power of the reflected signal. And so to recap our readout mechanism, as the incident infrared power changes, there's a change in temperature, which corresponds to a frequency shift. This frequency shift corresponds to a change in impedance at a fixed observation frequency. As the detector impedance changes, so too does the impedance mismatch between the detector and the readout. This changes the power of the reflected wave and therefore our output voltage. And we can characterize the sensitivity of our detector by its responsivity, which is given as the change in voltage with respect to incident IR power. And it can be written as a function of TCZ as shown here, where G is some constant related to the voltage gain of the circuit. And so therefore, in high quality factor resonators, we're able to achieve very sensitive thermal detectors. Okay, we have an additional advantage besides the enhanced sensitivity for impedance-based readouts, and that is unlike frequency-based readouts, which require either embedding each individual. The advantage is obvious when you consider scaling to arrays of detectors. So for frequency-based readouts, you have to either embed each detector in an oscillator circuit or feed them individually. But for an impedance-based readout, what we can do is we can apply a single tone observation signal and use it to excite all of our resonators simultaneously. We can then measure all the outputs using a convenient voltage simultaneously. And this allows simple arrays, and also there's no diminished, the array time constant is not significantly diminished compared to the individual resonator elements. So now that I've gone over the design of our detectors and readout, I'll share our experimental results. I won't go into depth about our fabrication process because that's pretty standard, and I'm running out of time for aluminum nitride MEMS. But one thing to note is that for the top electrode deposition, because the top electrode width defines our peak absorption wavelength, we define different resonators to have different top electrode widths and therefore peak absorption wavelengths, and I'll show that later. You'll notice some significant resonator warping in the resonator. This is due to some development of stress in the film, the aluminum nitride film, as it was sputtered. Our measurement setup consists of a CO2 laser with the beam path shown here schematically in red. The beam is passed to a beam splitter with half of the power measured by a broadband power detector and the other half sent onto the detector. We use an infrared camera to align the beam and the detector, and we illuminate the device under test using DC probes that apply current to heat the resonator. We can then apply an observation signal to measure the change in reflection coefficient via an RF probe. And so in order to get the optimal response, what we need to do is we need to determine the best observation frequency. And we do that by first measuring the impedance response, shown here. And from that, we can extract a quality factor of 870, which corresponds to a TCZ of 9.6%. And this TCZ is 2 to 3 times higher than the TCR for state-of-the-art microbolometers, such as vanadium oxide. And so we then measure the detector output voltage as a function of resonance shift. And we see that there's 2 linear regions on either side of series resonance. And we choose to operate in the linear regime to the right of series resonance, which is steeper because of the sharper impedance transition between series and parallel resonance. This linear regime corresponds to a 26 Kelvin temperature range, and we can extract this from our measured TCF. And we choose our observation signal to be near the beginning of this range, so that as the resonance shifts downward, the observation signal remains in the linear range for as long as possible. We can then extract the detector responsivity. We do this by measuring the voltage variation at the output as we vary laser power. And over that linear range, we see a constant responsivity of 33 volts per watt. This is well below what the ultimate responsivity we think we can achieve. And that is largely due to the fact that the commercial power detector we use in this proof of concept has a very low responsivity itself, which diminishes the responsivity of the detector. But we believe, based on our theoretical calculations, that we can significantly improve upon this, especially when you consider that our TCZ values are already 2 to 3 times higher than commercial TCRs. And that's with a fairly moderate Q of 870. And so we expect that we can enhance that by a further factor of up to 5. And so with that and a custom-built readout to replace this commercial detector, we expect orders of magnitude improvement in the responsivity. Thermal time constant is measured by modulating the modulating the laser and measuring the transient voltage response. We extract the thermal time constant at 400 microseconds, and we confirm that to the response by current heating the resonator, and we see very good agreement. The difference in amplitude between the current-driven and laser-driven responses is due to some power handling limitations within the thin top electrode trace that we apply the current through. So lastly, I'll talk about the spectral selectivity measurements. Here we show the absorption spectra for 3 different devices with different top electrode widths. And this verifies that we have lithographic control over the absorption wavelength. We measure these absorptions this reflectance with the FTIR. And we assume that the transmission through the resonator is negligible due to optically thick bottom electrodes. Therefore, the absorption is, all the energy that is not reflected is absorbed, and so we can determine that our maximum absorption is over 80%, as shown here. We confirm that transmission assumption in the FTIR measurement by directly extracting the absorption from our readout circuit. And we do this by exciting the detector and then varying the output wavelength of the laser. As the output wavelength changes, we measure the change in output voltage, and we can extract the absorption from that using the measured responsivity and the calculated power incident upon the detector. And we see excellent agreement between the extracted and the measured absorption with the limited number of data points due to discrete lasing wavelengths in our laser. So in conclusion, we've demonstrated a MEMS detector, a detector that fully hybridizes MEMS and aluminum nitride MEMS and metamaterial absorbers to achieve high spectral selectivity and fast response times. Although our responsivity value is not as high as it could be at the moment, we expect by optimizing our readout circuit and improving our fabrication process, we can have orders of magnitude improvement in that and improve upon the current state of the art. Additionally, our impedance-based readout permits the scaling to multiplexed imaging arrays that maintain the speed of individual detector units. And so I'd like to thank the Applied Research Institute at the University of Illinois for funding, and I'm not sure how I did on time, but I'll take any questions that time permits.